All right, we are back at it. So I'm going to go over class 2 exercise, and the instructions are here for you to read. But basically, I'm going to show a handful of concepts, and what I'm going to have you do, and I'm going to show them individually. And what I'm going to have you do is just also do them individually. But I'm not really providing you a data set to do them on. And so you'll see I've generated really fake, just contrived data sets that make it easy to see what's happening with the things that we're going to do, but aren't maybe super realistic. So your challenge is to find either find a data set or make a data set. And you could do one data set for all of the things we're going to do, or you can create a multiple individual data sets. You saw in our first activity that you can create data sets by typing into SPSS directly, or you'll see I've created CSV files using Microsoft Excel that I'll then read into SPSS. And so you can read it there. I'm going to ask you to just fill out a Word document. That'll be easy. And so you can use screenshots in order to do that. And so, okay, here are the topics that we're going to cover. And these are crazy useful topics. And they can be slightly tricky at times, but you'll see as we go. So switching over to my VMware Horizon, the editor here, and I'm just going to import data. And the first thing that we're going to talk about is duplicate values. So I'm going to bring this in. And again, usually things work out. We can examine if they don't. Something happened there that I don't like, and I figured out how to fix this. But it's the fact that it popped up. So, and if you've got your windows arranged like left and right, you don't want it to pop up. So I'd actually already deselected it. But what you want is this. If you go to edit and then options, there's edit and then options, and unclick this raise viewer window, that'll make things not pop up in random places. Which I like. You might like the surprise of where's my results going to come up. Okay, so in this data set, we have one variable, and you can see there are different values for the variable. We've got 1, we've got 2 2s, we've got 3 3s, 3 4s, a single 0, -1, -2, -3, -4. Oftentimes in data sets, we're going to wonder if a variable has multiple, is duplicate entries. And why might we do that? Well, maybe this variable stands for a student ID or a state or something where we should only see that thing once in the data set, and it would be a problem if we were going to see it multiple times. As another example, I was looking at a pregnancy data set, and some women have multiple births, and so each line was a pregnancy, and then the woman would be repeated, and we'd be interested in how many births the person had. So how many times were they duplicated in the data set? And so in order to see this, I'm going to go to data, and then I am going to go to identify duplicate cases. And I'll get this little pop-up here. And I only have one variable, so I'm going to define matching cases. I'm going to define if it's a duplicate just based on this one variable. Now, you could do this with multiple variables. You could say these 3 variables define a row. See if I have any duplicates of these 3 variables. And all of these features end up working. You can play around with that. I'm going to encourage you to use syntax. So here's our syntax editor, which is kind of wild. Let's get this over there. Let's get our output, and then maybe we can get our syntax just floating in the middle. I kind of like this workflow. And so I didn't run anything yet, but I put it into my syntax. And now I'm going to highlight. I'll click run. And you're going to see a few things happen. So first of all, let's look over here at primary last. And so if you really broke down these features here and looked at what was going on, you'll see that we're creating a new variable, primary last. And you might stop and look at this and say, what is primary last? Well, it is, for this variable, it's 1 if it's the last time in the data set that it sees it. So 2 showed up again. So 2, this was the last time it saw 2. This was the last time it saw 3. This was the last time it saw 4. And then all of these are unique, so they only see them once, so it's the last time. And it creates, this will be a pattern. It creates a variable to identify duplicates by, and then it summarizes them in the output. And so if I go over here, I get a couple of different measures. I get that we have 14 data points. There's 14 rows. I get that there are 5 duplicate cases. I have an extra 2, an extra 3, an extra 3. That's 3, 4, and 4 is 5. So I have 5 duplicate cases. I have 9 primary cases. A primary case being it's the first time that it sees it. And so now by creating this, by running this, I get to know how many duplicates I have, and I can identify where the duplicates are using this primary last variable. And so that's about duplicate cases. You can explore the features there. If you really dove in and looked up these different commands, you could understand how it's doing this. There's a bunch of code going on in the background that obviously this is a little bit more complex than some of the other stuff that we've looked at. Cool. What's next? So that was examining duplicate values. Oh, and I wanted to show you of how I would suggest to complete the exercise. And so I'm asking you to take screenshots. And so if on my Mac, so I'm using a Mac and looking at a Windows computer, I can hit Control Command Shift 4 and I get this screenshot thing. So what I would do is Control Command Shift 4 and then I'm going to copy this output. And this is what I want you to put in your exercise. So maybe you would create a new document. Got that typewriter keyboard, and you'd say 1, I use data on goats and pigs to look at duplicate values. Here are the results. And now I'm going to copy and paste my screenshot there. I also want you to include the data, so you could either send me the data or you could just copy and paste the data. Here is the data. And so if you say, so it can be a long document with lots of screenshots, but that's one way to do it. The other thing is if you want to actually do it within the windows, I think there's something called a snipping tool. So if you play around with the snipping tool, that's how you take screenshots within the actual windows. On the Mac, I find it valuable to actually do the work outside of the Windows environment and just take screenshots. You can also control or right click and then copy this actual thing into a Word doc, and that's another way to input something. But I basically want, for just looking at your work and giving you feedback, I want something that looks like that. Okay. The number 2, I should edit that out. If I don't edit that out, that's my bad. The number 2, we're going to talk about the idea of a merge or a join. And so I'm going to import 2 data sets here. Merge 1. And then I'm going to import merge 2. Now, so one thing you're going to notice right now, I have 3 data sets open, and SPSS will allow you to have multiple data sets open, which is kind of a cool feature. It'll continue to usually, unless you specify, it'll continue to have 1 output file and 1 syntax file. And so that's kind of a nice case. Now, everything's in order here. I'm actually going to, you can drag and shift the order around, and I'm going to do that because it's going to make the example a little bit more important. Okay, so here's the 2 data sets. On the left-hand side, I have the name of a person, Ben, Bob, Billy, Casey, and then I have their mother. These are very old-time names. These are all women in my family: grandma, great-grandma, grandmother, Joyce, Mildred, Marion, and Krista. And then over here, I have the sister data set. So on the left is the mother, on the right is the sister. And you're going to notice something. I have, for each person has 1 mother, but sometimes people don't have sisters. Ben doesn't show up here. Bob shows up once, so he has 1 sister. Billy shows up twice, so he has 2 sisters, and so on. And we want to come up with a way to, it's inconvenient to have this information in 2 separate locations. So we want to come up with a way to put this in 1 data set. And you might pause and think about, what would that data set ideally look like? Like, what would you want that data set to look like? I'm just going to type here as an example. So let's do mother and then sis. And so what would that data set look like? Well, for Ben, it would be mother is Joyce, and then he doesn't have a sister, so we wouldn't put anything there, right? Now, for Bob, Bob's mother is Mildred. His sister is Katie. That's easy. I'm running out of room here because the variable width, but you're with me. Billy has a mother named Marion. And then Billy has two sisters, Emma and Emily. And so what should we do? One thing is we could type Emma and Emily in this same cell. Another option would be to make another line for Billy, where one is Emma and the other is Emily. And that is typically the preferred way. So now each row is a name and a sister combination, and the mother is kind of duplicated in that way. And there's many different ways to put together data sets to merge two data frames. And what's ideal depends on what you plan on doing with it next. And so this will just kind of get our feet wet with whatever. I'm going to delete this for the example purpose. Clear this case. And so what I'm going to do is I'm going to do a merge. And the way this happens is if I go to data and then merge files, then you got to pause and think, do I want to add cases or add variables? I want to go from having two variables, name and mother, to three variables, name, mother, and sister. So that I'm adding a variable. If I had additional cases, if this other data set was also name and mother, and it was just different names and mothers, and I wanted to make it longer, I would add cases. If I want to add variables and make the data frame wider, I'm going to add variables. And so I'm going to do that. Now, select a data set from the list of open data sets to merge with the active data set. So I clicked data in here. So this is the active data set. And then I want to merge with, and you can see right here very faintly, data set 3 is what I'm looking to merge with. So I'm going to say, okay, data set 3. And it's going to create a new data set. And here are the variables that are going to go in that new data set: name, mother, and sister. And it's going to remove name because we don't need name twice. And so let's just try hitting OK. What happened there? What just happened? I just hit OK. I just went into the default setting. All it did was copy this sister column over directly. And so that's not what I wanted. It didn't pay attention to... Now Ben has a sister named Alex, but that's actually Alex's sister. That's kind of messed up. So let's clear that. Let's try again. Take 2. Data, merge files, add variables. We want to make it wider. I'm going to go data set 3. Now, I'm going to match cases on key variables. And I'm going to say the keyed table. It's asking me about a keyed table. Well, what a keyed table is saying there's a lookup value, a one-to-one relationship, a lookup value. For every name here, there's one mother, and I can go look it up and grab it. And so I might try that. Let's just see what happens. Let's say the active data set is a keyed table. It looks like for every name, we have one mother. And then our key variables. What a key variable being, what are we matching on across the tables? Well, we're matching on name. We want to connect these by the name. Click OK on that. What happened? I got an error. Oh no. Warnings. Duplicate key in a table lookup must be uniquely identified in the table lookup file. So it must not like that I have these duplicates here. And so the solution ends up being Stata, and I think it's silly that it needs this, but Stata needs the cases to be sorted by the variable that we care about. So I'm going to sort, things got funky because I added stuff in. So I'm going to sort both of them by name. Data, sort cases. Cases are rows. Again, it got funky because I was doing some random stuff. But if you didn't do weird stuff, you should get something like this. And now the answer for our problem is going to be to merge files, add variables. I want to merge with dataset 3. My key variable is, match cases on key variables. So I'm going to match based on name. So let me put name in there. And then if I just did this, and this is going to open up an additional option. Cases are sorted in order of key variables in both sets. Yes, I sorted in order of name here, and I sorted in order of name here. Cases are sorted in order of key variables in both data sets. Both files provide cases. Yes, there's a name column in each of these. And so let's do the paste thing. And so it should have come up in the syntax. And so now I have this syntax for the match. I could have just hit run, but kind of like it. As we start to want to look at the different syntax. So activate dataset 2, that means I'm starting here. I'm matching with dataset 3. I'm starting with star, refers to the open dataset, and then execute means do your thing. So let's run that. And so this looks pretty good. Duplicate key. It's giving me a warning, but the beauty of this small data set is that with this, I can check to see what happened. I can take a look. And it actually looks pretty good. So Ben Joyce doesn't have a sister. That makes perfect sense to me. Billy's mom is Mary and sister is Emma. And now I have this new row 3, Billy. And then it didn't put Mary in there. It didn't keep Mary in, but it added Emily, which is the right sister for Billy. And then Bob has a sister named Katie, Mildred Katie. And then Casey has 3 sisters, Alex, Amy, and Alex. I guess I have duplicates there from something I had done. Now, the only thing that we might not like about this is we might want it to look like this. Right, we might want to always know what the mother is, and we can talk in the future about how to make that happen, but this should kind of wet your whistle when it comes to merging files and the flavors and what you might want to get to. And again, your final output's going to depend on what you want. The ideal and the simplest case is where there's only one, the name is unique here. There's only one here to go back to our looking at duplicates, and then there's only one name here, and then we're literally just finding the value and looking it up, and we're not going to create additional rows or make it longer or anything like that. Okay, so the idea of a merge/join, your task will be to create some sort of CSV or something to join with and play around with that. Now we're going to go into calculating correlation. It's a little bit disjointed, this little, I'm going to just clean up. No. All right, now I've got one data set open, and let me put this is how I like, when I have to work on one monitor, this is how I like to do it. So now I've got this. Now I'm going to open a new file, which is going to be my correlation data. Let's get it. And again, I don't have a context really here. I just have 3 variables, X, Y, and Z. And what a correlation does, if you're not familiar, if you're a little fuzzy, is it allows you to determine the strength of a relationship between variables. It says, how close are these associated? However, there's a key point here, is it only measures the strength of a linear association. It looks at how well does a line describe these data. How strong is a line that goes through the data? And so let's take a look. The first thing that's pretty valuable is to look at the scatter plot. And I'm going to look at the matrix scatter. So a simple scatter will show me 2 variables, maybe X versus Y. A matrix scatter is going to let me look at multiple different scatter plots for multiple different variables at a time. I'm going to say, I actually want all of X, Y, and Z in here. And again, there's always additional options that you can play around with and check out, but we'll go with the basic thing here. And so in my output, I now have this scatter plot matrix. And so how do I read this? Well, in the top right is X and Z. So X is on the Y axis, Z is on the X axis, and it's plotting these points. So what would this point be? It's the largest value of Z and the lowest value of X. This must be 1, 8. And 8 is the X coordinate. 1 is the Y coordinate. So this is the ZY. Now, why WHY? Why don't we have anything on these diagonals? Because this is looking at the relationship between X and X. Of course, X always equals X. So plotting that serves no use. And so we can look at how strong of linear relationships does it look like we have. It looks like if I look at here, X and Y is pretty strongly linearly related in a positive way. Here, X and Z is pretty negatively linearly related. I could draw a pretty good negative line through those. Z and Y maybe a little less so, it's a little scattered, but I would definitely draw a negative line. And so what I'm doing is kind of informally approximating what I think the correlation would be. We can do better though. I can go to analyze, I can go to correlate, and there's, if you looked on Wikipedia, you get messiness about all these different types of correlations. Most people just use the bivariate correlation. And I'm going to say, what are the correlation for all of these things? So when I run this, I'm going to get kind of a similar scatter plot matrix, a scatter plot, but of correlation measures here. And so the correlation between X and Y is 0.903. And it's positive because the relationship between X and Y is a positive relationship. This is a 0.903 correlation. That's pretty strong. 1 is the highest you can get. And it does, we can talk about hypothesis testing later, but it ends up being statistically significant. This is a p-value of 0.014, saying it's likely not the case that we would see a correlation like this just due to random chance. There's only a 1.4% chance that we would see a correlation like this, just a random chance if we were to randomly select 6 values of X, 6 values of Y. So we can be pretty sure that there's a positive correlation there. Let's look at one more. Y and Z is negative 0.886. That's also significant, but this one's negative. Y and Z. Well, I can look at it here. This is Y and Z, or I can look at it here. This is Y and Z. You can see these two plots are just inverted, the X and the Y axis, because we're both looking at Y and Z. Just now Y is on the X. Here Z is on the X. And that makes sense to me. Negative correlation there. Pretty strong, negative 0.886, maybe a little bit less than the X and Y correlation. This one's a little bit tighter than this one. That makes sense to me. And so this is the basics of how you calculate correlations. Here's the correlation between X and Z, negative 0.751. And I just wanted to, I don't know the degree to which you have background with correlations, but there's a couple of cool images here that I think help with intuition, and they show examples. The strongest correlation is the closer you get to 1 or negative 1 is perfect correlation. So this is a line literally exactly goes through all of these points. It's a positive line. Here's a negative line, literally goes exactly through all of those points. No correlation is, I can't draw a line of any significant meaning. It would just end up being a flat line, and the flat line's not going to do anything for us. Low negative. Yeah, negative line goes through here. Negative 0.5 is the correlation. Negative line goes through there, but it's not very tight. It's a little bit scattered. Here's the same thing with positive. Now, to make the other point that I was talking about. Oh, did I open up? Oh, shoot. I wanted to. Wikipedia correlation. I thought I had this other one pulled up and ready to go. Oh, that's exactly what I wanted. Let me just update that link quick. And so here makes that exact same point. And these are all, you can look at these correlations, and these are kind of what we had talked about before. But all of these down on the bottom are correlation of exactly 0. And you might think that might seem weird to you because it certainly looks like there's a relationship here. It looks like if you tell me the X value, I can predict the Y value probably pretty well. It goes down and up, then down, then up. Here's a nice little, I don't know, cantaloupe, muskmelon, double cantaloupe or a double moon, donut, whatever. You have what appears to be relationships and what appears to be sensible data here. However, remember, it's a line. If I was going to draw a line through here, I can't draw a meaningful line. Same here, same here, same here. It would go up then down, but I can't. It's a line. It can't go up then down. And so I end up just with this flat line. And so you can think of a 0 correlation of whenever your best line would just be a straight across flat line, that's 0 correlation. You don't really have a line that fits. And so keep that in mind whenever you think about correlation. Let's move on to t-tests. It's t-test time. T-test time, our favorite time of day. Okay. import data. I've got examples here. And I don't have really a context for this data, but I'm going to show you what does a t-test do generally. What in the world is a t-test? Well, it compares the means of two distributions. And so what do I mean by that? I mean that let's run one and we can talk about it. Where is it? Compare means. And let's start with, there's a few different type, and so we'll start with this. So independent samples t-test. I'm going to test the variable x. And here I'm going to put, for an independent samples, I'm going to make a grouping variable treatment. And basically I'm saying if you're in 0, if you're treatment 0, you're in one group. If you're treatment 1, you're in a different group. And I'm going to compare the means for variable x. So the mean of 4, 5, and 4, I think is 4.67 on the zeros. So I'll have a 4.67 here. The mean of this, what's the mean of 3, 8, and 7? That's 6. So here I have 6, here I have 4.67. And I'm wondering are these means statistically significantly different? And that's what this t-test is going to tell me. So I click OK. And first of all, well, I got it wrong. It's 4.33. That's silly. 2 4s and 1 5 should be 4.33. That's not me. And then the treatment for 1s, the x is a mean of 6. And what this does, so the difference in our means is negative 1.667. And there's two different assumptions where if I assume equal variances or not, or if I don't. Let's not worry about that for the time being. But what I'm going to pay attention to is these p-values, the significance of 0.346 and 0.390. And that again tells you the percent chance that we might see this from randomness. And if that's below 0.05, we're going to say if it's less than a 5% chance we're going to see this from randomness, then they're probably different. But here there's a 39% chance that if we had just randomly selected 6 points, we might, and then put them into 2 separate groups, we might see something like this from randomness. And so we're going to say, no, these aren't statistically different. We're not sure that the mean of 4, 5, and 4 is significantly less than the mean of 8, 7, and 3. There's just too few data points. There's randomness when I grab data points. And so I'm not sure that the means are different. Maybe these are 3 test scores of guys and test scores of girls. And we just can't say that girls perform better than guys because we only have 3 data points. They're actually not that far apart. Here, the lowest one is actually within the girls, but so is the highest. So we have a higher spread. This translates into the higher standard deviation in the treatment of 1.528. And so this was the independent samples t-test, and it compared for one variable, and it grouped by something. It grouped by the treatment. There's a few different other types of data, of ways of comparing means. Let's do a one sample t-test. And so here, I'm going to look at the full distribution of x, the 4, the 5, the 4, the 8, the 7, and the 3. And I'm going to compare this to a fixed value. I'm going to say, I want to know if on average these numbers, maybe these test scores, are larger than a value. We know that the mean of the first is 4.33, the mean of the second 3 is 6, so the mean overall is maybe 5 of the whole thing approximately. Let's see if that's significantly higher than 3. Encourage you to pause and kind of stop and think about what that means, or if you think that the p-value is going to be. So I'm going to run this, and here's what it tells me. It tells me that the mean of x is 5.17, gives me a standard deviation, And then this is the test value of 3 comparing to the value of 3. And my statistical significance, my p-value is 0.041. So there's a 4.1% chance that we'd see something like this based on randomness, see something this extreme different from 3 or more extreme if the mean was actually 3. And so we're going to say, no, that's probably unlikely the case. We can reject this null hypothesis that the mean is 3. It's likely bigger than that. And what would our best guess for the mean of these numbers be? It'd be 5.17, but that's not necessarily, that's not the right value. We just know that it's bigger than 3. And so we're able to look at that. And that becomes useful. Let me show you the last way of comparing means, which will be a paired samples t-test. And what's a paired samples t-test? Now it's going to look at by row going from X to Y. Going from X to Y. So maybe this is a student's pre-test and this is the student's post-test. This person increased 5. This person increased 2. This person increased 4. This person increased 0, and so on. And we're going to pair these and do a t-test here. And so paired differences. The mean is negative 2.833. Now, why is that? It's because the way I did my grouping, I went X minus Y. And so this is negative 5, negative 2, negative 4, negative 6 to the computer. It's symmetrical, so it doesn't matter. But if you took the mean, it'd be 2.833 as opposed to negative 2.833. And again, it's comparing this value to 0. It's saying, hey, on average, do these numbers change? Do these change on average in some systematic way? And it does look like they systematically go up in the way that this is coded X minus Y. They systematically go down, and my p-value is 0.042. So there's only a 4.2% chance that I'd see something this crazy or crazier if the mean actually was 0, if the mean difference was 0, if this pre to post X to Y actually didn't change at all, there'd only be a 4.2% chance that I would see something kind of this crazy, systematic differences this positive or this negative if I look at this. So that's a paired sample t-test. Now, I want to show you an equivalence between a paired sample t-test, and I've actually calculated these differences. And so the other way that we can look at this is compare means, one sample t-test. I'm going to compare Y. This is equivalent. Oh, gosh. Mobby. This is equivalent to, there's a simpler way to ask this, which is just to say, hey, does Y minus X, is that greater than 0? If I'm changing something, my Y minus X should be greater than 0. And it should be statistically significant when I compare these means. So I'm going to click OK. And you're going to notice I get similar information. The mean of Y minus X is 2.83. The mean of X minus Y was negative 2.83 with how we define things. Standard errors match up. The significance level of 0.042 matches up. And so this is a equivalent way to compare X and Y and look at, hey, are these differences systematic versus what if I calculate the difference and ask if each of these is statistically different from 0? And so I'm just going to give you a summary here. So I go to compare means. One sample t-test takes one value, one set of values, and compares it to a number that I give it. Independent samples t-test was the first thing that we did, where we used that treatment variable to split up X and X. We looked at the one variable X and we split it into treatment 0 and treatment 1. And then we compared the means within there. Paired samples t-test was where we looked at X and Y and we said these are pairs. This first X value is paired to this first Y value. And we looked at that. And then I also just lastly showed you a way to use the differences we calculated between X and Y to calculate a one sample t-test. Cool. Last thing, creating and summarizing indicators. And so for that, let's open this up. One thing you might want to know, I have a data set with X and Y. One thing you might want to know is how many or what percentage of the X values are greater than 0. And we have a 4-row data set, so that should be obvious. It's 3 out of 4, 75%, 3 of them. But if I have thousands of rows, that would be very difficult. And so how might I do that in a systematic way? And there's a 2-step process to this. We're going to create an indicator. We're going to create a new variable that tells us if X is greater than or equal to 0. And then we're going to summarize that. We're going to say, what's the characteristics of that new variable? So let's go to transform, and I can X then 0. And I'm going to take the variable X, and I'm going to say, hey, are you greater than 0? Let's paste this. Incorrect variable name. What? I don't know what happened there. Using the... And so now I have 0 when it's not and 1 when it is. And so what could I do here to figure out how many are greater than 0? So I created the indicator, and now what I'm going to do is I'm going to summarize this. And so we'll summarize X greater than or equal to 0. I'm going to want the mean and the sum are going to be the 2 interesting values here. We'll click OK. Down here, I get 3 for the sum. So that tells me how many values are greater than 0. And then you're going to notice that the mean is 0.75, which is exactly the percentage of X values that are greater than 0. And so let's think about that for a second. Why is the mean of these numbers the percentage greater than 0? Well, think about what the mean does. Is it adds up the values. So if I sum these, I get 3. And then it divides by how many there are. There's 4 of them. And so if I end up summing up the number, I get 3, which is the... Well, think about what is a percentage. It's the number greater than 0 divided by the total number. So the numerator in that, the top number, is the number greater than 0. Well, that's exactly the sum of the zeros and ones. Contribute 1 each time. I sum those. The numerator's the number that are greater than 0, which is 3. And then what's the total number of values? Well, it's the count. It's the total number, which is 4. And so I end up doing 3 divided by 4, which is 0.75. And that's a really useful thing to keep in mind, is anytime when you take zeros and ones, something binary, and I take the mean of it, I get the percentage of ones in that column. We'll do one more. Let's do X greater than 0 and Y equals 3. You might notice something. This looks wrong, right? This second value is 0, but X is greater than 0, and Y does not equal 3. So that is right. I thought this would produce something of interest. Let's actually do one more that actually gives us some values. If we do X greater than, let's do X greater than 0 and Y equals 4. This oughta. I didn't change the name of it, so it's a very misleading name. But again, now I have the 0, 1, 0, 0. I click OK, and I now get, I guess I didn't ask for the mean here, but I get the number of values. What I wanted was descriptives, options, I get this 1, and then that's 25%. Total is 1 divided by 4. There's 25% of them are x greater than 0, and y equals 3. All right, that is all the new content for class 2. We're going to put this together in what I think is a beautiful way in our in-class activity. So you make sure you have a decent idea on each of these concepts and come ready to think hard and put these together in what I think will be a cool context. Your exercise, which I hope you were doing as was happening, was and is to create each of these with a data set of your own or a data set that you find, and go from there. See you soon.